Hey everyone, welcome back. Before we dive deep into one of Earth's most defining and utterly unique features, I'm sending out massive waves of positivity and heartfelt wishes to all of you watching. Seriously, wherever you are in the world, I genuinely hope you're feeling fantastic, taking amazing care of yourselves, and staying healthy, because appreciating our incredible planet starts with taking care of the life it sustains. Now, let's talk about something truly fundamental to who we are and where we live. Look around you, see those mountains, those ocean trenches, those vast continents? They're not frozen in place forever. Our planet is alive beneath our feet in a way no other world we've found seems to be. Here's the astonishing truth: Earth is the only planet we know of, anywhere in the universe, that has active plate tectonics. Yep, you heard that right. While other planets might have volcanoes or quakes, only Earth has this grand, global conveyor belt system where its entire outer shell is broken into giant, slowly moving plates that constantly jostle, collide, dive, and create. It's not just a geological quirk, it's the engine that shapes our landscapes, regulates our climate, and might even be a key reason why life thrives here. Forget static globes, Earth is a dynamic, evolving masterpiece, and plate tectonics is its heartbeat. So, what exactly is plate tectonics? Imagine Earth's outermost rigid layer, the crust and the very top part of the mantle, isn't one solid shell like an egg. Instead, it's cracked into about a dozen gigantic pieces, like fragments of a broken eggshell. These massive slabs are called tectonic plates. But here's the crucial part: they're not sitting still. They're constantly on the move, gliding very slowly over a hotter, softer, more malleable layer of rock beneath them called the asthenosphere. Think of the plates like thick, cold rafts floating on a layer of warm, slowly churning putty. This movement is incredibly slow by human standards. Plates crawl along at speeds comparable to how fast your fingernails grow, maybe a few centimeters per year. But over millions of years, those tiny movements add up to distances larger than continents. This slow-motion dance isn't random, it's driven by the intense heat deep within Earth's core and mantle. That heat causes the rock in the mantle to convect, hot material rises, like bubbles in a pot of almost boiling water, cools down as it nears the surface, becomes denser, and then sinks back down again. These massive, slow-motion convection currents act like giant conveyor belts, dragging the plates along with them. It's the planet's internal heat engine powering the movement of its surface. Now, what happens when these plates move? That's where Earth's dramatic landscape comes from. Plates can interact in three main ways, and each creates distinct geological features. First, they can diverge, or pull apart from each other. This mostly happens under the oceans, along giant underwater mountain ranges called mid-ocean ridges. As the plates separate, hot magma from the mantle wells up to fill the gap, cools, and solidifies into new oceanic crust. The Mid-Atlantic Ridge is a prime example, slowly pushing North America away from Europe and Africa. Second, plates can converge, or crash into each other. This is where things get really spectacular. If one plate carries dense oceanic crust and meets a plate carrying lighter continental crust, the oceanic plate usually dives down beneath the continental plate in a process called subduction. This creates deep ocean trenches, like the Mariana Trench, the deepest point on Earth, and fuels massive chains of volcanoes on the overriding continent, like the Andes or the Cascades. If two plates carrying continental crust collide, neither wants to sink easily. Instead, they crumple and thrust upwards, creating towering mountain ranges like the Himalayas, which are still rising today as India slams into Asia. Third, plates can slide past each other horizontally. This happens along features like the San Andreas Fault in California. Here, the plates grind past each other, building up immense stress that's eventually released as earthquakes. Every mountain range, every deep ocean trench, every major earthquake zone, they are all direct results of these plate interactions. Earth's surface is constantly being recycled, reshaped, and renewed. Why is Earth seemingly alone in this? We've sent probes and telescopes to study thousands of planets and moons. Venus, similar in size and sometimes called Earth's twin, shows evidence of past volcanic activity and some surface deformation, but no clear signs of current, global plate tectonics like Earth's. Its surface appears much younger in some places and older in others, suggesting it might have undergone catastrophic resurfacing events rather than the steady, piece-by-piece recycling Earth has. Mars, smaller and cooler, has the solar system's largest volcano, Olympus Mons, and a massive canyon system, Valles Marineris, but these seem to be features built over stationary hot spots or formed by ancient stretching, not evidence of moving plates. Its surface is essentially one giant, rigid plate, a single tombstone for ancient geological activity. Mercury and the Moon are geologically dead worlds, their surfaces heavily cratered and unchanged for billions of years. Even large moons like Jupiter's Ganymede or Saturn's Titan show fascinating geology, ice tectonics, cryovolcanoes, but nothing like the global system of interacting rocky plates we have on Earth. The icy shells of moons like Europa might have shifting plates of ice, but this is fundamentally different from the silicate rock plate tectonics of Earth. So far, Earth stands unique. Scientists believe several key factors had to align perfectly for plate tectonics to get started and persist here. Size and heat are paramount. Earth is large enough to have retained significant internal heat from its formation, accretion heat, and generates more through the decay of radioactive elements like uranium, thorium, and potassium in its core and mantle. This heat is the engine driving the mantle convection that moves the plates. Smaller planets like Mars cooled off much faster, their internal engines sputtering out early. Water is likely the magic ingredient. It might seem counterintuitive, but water trapped within Earth's rocks, subducted deep into the mantle, plays a crucial role. Water acts as a powerful lubricant and dramatically lowers the melting point of rocks. This lubrication helps the plates slide more easily over the asthenosphere and facilitates the subduction process itself. Wet rocks are weaker and more likely to bend and sink. Without water, the rocks might be too strong and brittle, preventing the plates from moving or subducting effectively. Think of trying to slide 2 pieces of dry sandpaper versus 2 pieces wet with oil. Venus, although similar in size, is thought to have lost most of its water early on due to a runaway greenhouse effect. Its surface rocks are likely much drier and stronger, potentially locking the planet into a single plate mode. Composition matters too. Earth has a distinct, rigid outer layer, lithosphere, overlying a softer layer, asthenosphere, the right kind of layering for plates to form and move. The exact recipe of rock types and their behavior under immense heat and pressure creates the necessary conditions. It's possible that plate tectonics started on Earth only after the planet had cooled sufficiently to form a rigid outer shell, and perhaps after a significant impact or other event helped break that shell into plates. Once started, the presence of water likely kept the process going in a self-sustaining cycle for billions of years. Plate tectonics isn't just about making mountains and causing quakes, it's arguably the single most important process making Earth habitable. It acts as Earth's ultimate recycling system and climate regulator. The carbon silicate cycle is the planet's natural thermostat. Here's how it works. Volcanoes, powered by plate tectonics, especially at subduction zones and mid-ocean ridges, release carbon dioxide, CO2, into the atmosphere. This CO2 traps heat, the greenhouse effect, warming the planet. Rain washes some of this atmospheric CO2 out, forming weak carbonic acid. This slightly acidic rain falls on rocks, weathering them chemically. The weathering process pulls CO2 out of the atmosphere and locks it into minerals dissolved in water. Rivers carry these dissolved minerals into the oceans. Over time, these minerals are incorporated into the shells of marine organisms or settle as sediment on the seafloor. Eventually, through the relentless motion of the plates, this seafloor sediment gets dragged down into subduction zones. As the plate dives and heats up, the carbon-rich sediments get cooked, releasing the CO2 back into the atmosphere through volcanic eruptions millions of years later. This cycle keeps Earth's temperature within a range where liquid water can exist. Without plate tectonics constantly recycling carbon, CO2 could build up uncontrollably, like Venus, or get permanently locked away, freezing the planet solid. Plate tectonics also plays a vital role in generating Earth's magnetic field. While the field is primarily generated by the churning of molten iron in the outer core, the movement of plates and the subduction process help regulate the heat flow from the core outwards. This heat flow is essential for maintaining the core dynamo. Furthermore, the constant renewal of the crust through plate tectonics brings valuable nutrients and minerals to the surface, contributing to the chemical diversity essential for life. It also creates the diverse environments, mountains, valleys, continents, oceans, hydrothermal vents, that have fostered the evolution of complex life. The story of plate tectonics is also the story of Earth's deep time. The continents we see today are not fixed. They are fragments of ancient supercontinents that have assembled and broken apart multiple times over billions of years. The most recent supercontinent, Pangaea, broke up starting about 200 million years ago, drifting apart to form the continents we recognize today. The Atlantic Ocean is still widening as the Mid-Atlantic Ridge adds new crust. The Pacific Ocean is slowly shrinking as its floor is subducted beneath the continents surrounding it. The Himalayas are rising as India continues its northward journey. California is slowly sliding north relative to the rest of North America. Plate tectonics provides the unifying framework to understand Earth's entire geological history, the formation of mountain belts, the distribution of fossils, the locations of mineral deposits, and the patterns of ancient climates. It shows us that our planet is in a state of constant, albeit slow, transformation. The map of Earth millions of years in the future will look vastly different from the one we know today. Continents will collide again, new oceans will form, and mountains will rise where plains now lie. It's a perspective that humbles us, showing that human history is but a fleeting moment in the grand geological narrative written by the movement of the plates. So, the next time you feel the ground solid beneath your feet, remember that it's part of a giant, ever-shifting puzzle. That familiar landscape of mountains, valleys, and oceans is the direct result of a unique planetary engine, plate tectonics. It's the process that recycles our crust, regulates our climate, fosters life's diversity, and continuously reshapes our world over millions of years. While we gaze at other planets and wonder about life beyond Earth, we should also marvel at the incredible, dynamic system right here that makes our existence possible. Earth isn't just a rocky ball floating in space, it's a geologically vibrant, living planet with a restless surface driven by the heat of its core and lubricated by the water in its rocks. Plate tectonics is Earth's signature feature, setting it apart in all the cosmos we've explored so far. It's the reason our planet breathes, grows, and evolves. It's the silent, powerful force beneath our feet, constantly remaking the world, reminding us that even the ground we stand on is part of an extraordinary, ongoing journey. Thanks for exploring the moving ground with me today. Stay curious, stay healthy, and take a moment to appreciate the incredible, dynamic planet we call home.